Hi, I'm Aruf Ayman, a PhD student at IIT Ropar working in the area of meta-learning. Today, I'm going to present my work, Adversarial Projections to Tackle Support Query Shifts in Future Learning. This is a joint work with Bharat and our supervisor Narayan Krishnan. First, I'll begin by introducing meta-learning and give an overview about the distribution shifts in meta-learning. Then I'll begin with the proposed approach and the results supporting the proposed approach. Then I'll conclude the discussion with limitations and future work. Humans are intelligent creatures and learn new concepts very quickly. If a child sees a horse in his comic book, he can identify a real horse even with mere experience. However, humans leverage previous skill to learn new or sophisticated skills. Is it possible to impart such characteristics to the machine learning models? A model which generalizes to new tasks and environments quickly that it had never seen at the time of training. So we aim to learn from the few shots of experience. And meta-learning means learn to improve the learning process itself. In conventional supervised learning, we have a training pool of data and test examples. All correspond to the train and the test classes are same, but the instances are different. In meta-learning, we have two phases, meta-train phase and meta-test phase, containing disjoint classes. And each data point is a task, which is a learning problem, comprising of a support set and a query set. Each task has an n classes and k examples corresponding to each class. The task-specific information is gathered from support set and task-agnostic from the query set. A critical assumption in meta-learning is that the train and the test tasks belong to a common distribution. The bad news is that different tasks need to share the common structure, but good news is that there are many tasks which share this same structure. Say the different types of bottles have a common process of opening the lid. Recently, this assumption has been challenged and the settings have been proposed where meta-train and meta-test sets correspond to different distributions. Here, meta-train set corresponds to realistic images while meta-test has sketch images. This area is called as cross-domain few-shot learning. However, we are interested in the distributional disparity inside the tasks. A recent work has been published which proposes this setting. Here, the meta-train set, the support set of meta-train set has real images while the query set has mask images. And for meta-test set, support set contains sketch images while the query set has caricature images. So there are distributional disparities between the support and the query sets of the meta-train and meta-test set. But practically, the perturbations are taken as the distributions. And they have been taken from Hendricks et al., which comprise of which formulate the different types of noises as perturbations. Say in meta-train set, we have Gaussian noise or impulse noise in the support and the query sets. And during meta-testing, we have say scatter or speckle noise. So these forms of noises, although they are disjoint, but yet they are related. We propose a different setting which we call SQS plus, which is harder as it has unknown distribution shift at the time of meta-testing. During meta-training, it does not have any distribution shift. The support and query images in the meta-train set all come from realistic images, while there is a distributional shift between the support and the query set in the meta-test phase. Practically, only meta-test images are perturbed with the disjoint distributions for the support and query sets like spatter noise or saturate. As the model is subjected to unknown meta-test distribution shifts, it makes our setting more realistic, which is indicated by the prototypical network's performance on the mini ImageNet on all these three cases when there is no support query shift for the case of SQS and our proposed setting SQS+. The optimal transport approach has been used to tackle support query shift by projecting the support set onto the query set in the future space. However, the issue with the optimal transport is that it requires transduction. That is, the meta-test query examples need to be available. We, on the other hand, propose an adversarial query projection, which is an inductive method to learn a model robust to both support query shift as well as SQS+. AQP simulates non-uniform support query shifts during meta-training to make the model robust to unknown shifts that may occur during meta-testing. Specifically, we augment the query data such that the meta-model's loss is maximized. Let TS0 and TQ0 be the original tasks. We aim to find a new query set, TQ, which lies in the Wasserstein distance from the original query, TQ0, such that the meta-model's loss is maximized. Practically, we estimate this worst-case query set by gradient ascent on the original query set. The new task comprises of the original support set and the augmented query set, which have distributional disparities. Therefore, the model can reduce the query loss only if it learns to extract the shift invariant features. The proposed AQP is an adaptive plug-and-play module which can be added to any episodic regimen. We have appended it to the prototypical networks and matching networks and shown results on CIFAR 100, Mini ImageNet, Tiered ImageNet, and feminist datasets. We observe that AQP performs better than inductive version of the optimal transport. Our major limitation is that we have considered simple perturbations like noises, but in future we wish to address more realistic distributional shifts like from sketch to caricature images. Thank you.